All right, so now we're going to derive an equation to solve for the de Broglie wavelength using the kinetic energy of something in joules. So we have two equations that we know. We have the EK is equal to 1/2 mv squared, our kinetic energy equation. We also know that the wavelength equation, de Broglie's wavelength equation, is equal to h over mv. So we see a common mv in both of these. One has an mv squared, one is just an mv. So to make them both the same, we're just going to multiply one of them by mass. So in this case here, I want to multiply mass on both sides. So I'm going to multiply by mass. Whatever I do to one side, I must do to the other. And we're left with an equation that looks a little bit different. Mass times EK is equal to 1/2 mass squared velocity squared. What we can then do is isolate for the mv. So if I get mv by itself, which is mv, m squared, v squared, it's the same thing, it's just mv squared, is then equal to 2m ek, or mass times velocity is equal to the square root of 2 times mass times ek. Okay, so now that I have mass and velocity isolated on the one side, we can then substitute that in for the mass velocity here. And we're left with the wavelength is equal to Planck's constant divided by 2 mass times ek, and then square root. So we can use this equation for the rare cases where you know the energy in joules and you want to then solve for the wavelength of that particle. All right, let's jump to the next one. So this is where the video comes into play about the double slit behavior of particles versus waves. So if you imagine, when we talk about our double slit, we're talking about the scenario where we have a small opening, something like this. And if you were to shoot just particles like the marbles, and you shoot them across, you'll notice that if it shoots too high, they'll just bounce back. If you shoot too low, it'll just bounce back. If you shoot it right in the middle, it probably will also bounce back. But the certain ones that shoot directly through the openings will then pass through, and then on a detector sheet, a screen perhaps, you would end up seeing a certain bright spot here and a bright spot here. You would have two bright spots, both of them directly behind the source. So once again, if I were to kind of color this in, you would have two spots that were bright directly behind. Once again, this is on some material that was like phosphorescent, that when it's struck by the electrons, it would then glow. Okay, so we've done that in terms of electrons. This is what we can see with particles. But now we're going to talk about them as waves. So what we're going to imagine is that the electrons are no longer just particles, but these little electrons are actually acting like those waves that we've done before, kind of like the light particles. So if you have that same situation where we have one opening and another opening, we have their double slits that we talked about. In this case here, we end up getting interference. We end up getting diffraction, that as the electrons go through these openings, they do not just simply produce two bright spots on the end like electrons would, particles would, but instead we end up getting that same diffraction pattern that we saw when we shot waves through this same apparatus. We see that we get this kind of a spreading out effect from one opening, the spreading out effect of the other, that these electrons are now acting what we're going to call as probability waves as they go across. And because of that, we end up getting this curve effect. We end up getting a large probability of the electrons existing directly behind the center of those two. A spot where you'd probably expect there to be 0 electrons. And then we get another wave that looks something like this. We end up getting spots of bright. We have a central max, followed by a first order max above and a first order max below. So this is the same effect that we had with the waves. So now these electrons are no longer just particles. These electrons are acting like waves, and this is what we're seeing. So if you take a look at that Dr. Quantum video, it's a great example of electrons acting differently depending on the scenario. It's mentioned in the video that the electrons, when they knew that someone was watching it, the electrons acted like particles. When the electrons had no sense and we're just looking at the results of it, the electrons then act just like a wave. We get this weird concept. This is the whole quantum idea. It's extremely strange, and that's okay.